Back to the QSD YouTube channel. Today I'll be explaining the physics diagnostic quiz for week 1 for the diagnostic periodic. The material for this quiz is chapter 1 and chapter 2. Let's start. Which statements describing evaporation are correct? Look, evaporation, I'll just summarize it as evap, is when a liquid goes to a gas, becomes a gas by heating it. Evaporation itself, like, there are two separate processes where a liquid becomes a gas, and in both cases the liquid evaporates. Let's just get that out of the way. But evaporation at base occurs at any temperature, and it causes the temperature of the liquid to drop. But at the boiling point, evaporation takes place anywhere in the liquid. But meanwhile, when it's at any temperature, it can only be at the surface of the liquid. Number 2. A sample of 70 grams of steel, specific heat capacity 385 joules per kilogram Kelvin, is heated from 20 degrees Celsius to 80 degrees Celsius. The quantity of heat needed to raise the temperature of this sample is, okay, look, Q, when it's a change in temperature, only a change in temperature, is equal to mass times specific heat, which is C, times delta T. Now for the units, for mass it should be kilograms. C, it depends on what they're asking for here. Since in this case they're asking for kilojoules, then here it should be in kilojoules as well. So kilojoules here, and then change in temperature, it doesn't matter. So 70 grams to kilograms, so 70 times 10 to the negative 3 to convert it to kilograms, times 385, again times 10 to the negative 3, because we need it in kilojoules, not joules, times change in heat, which is final minus initial. 80 minus 20 is 60. Now I'm gonna plug that into the calculator. 70 times 10 to the negative 3 times 385 times 10 to the negative 3 times 60, which will give us 1.61, or 1.6 rounded to one decimal place. Number 3. Below is the temperature time graph of a sample of matter being heated. Drag and drop the correct terms from the box below. The phase change of the sample occurs between the time interval. Okay, look. When a phase change happens, that means in the graph it's gonna be horizontal. Just let me make this thicker. It's gonna be the horizontal part. That's when the phase change happens, and that's between 2 and 8. Number 4. The boiling point of mercury is 357 degrees and its latent heat of vaporization is 300 kilojoules per kilogram. The energy needed to completely change a 0.15 kilogram sample of mercury from liquid into gas at 357 degrees Celsius is. So look, what they're asking here is how much energy is needed to boil mercury. That's it. And then when they're asking for boiling or like a change in state, energy is always going to be equal to only a change in state, because in the final they gave us a change in state and a change in temperature, but here we're only speaking about a change in state, right? So only a change in state would be the mass in kilograms times the latent heat of, in this case it's vaporization, which is boiling or condensation, and then there is of fusion when when the object melts or freezes. Okay, and here they gave us the mass in kilograms, so 0.15 times 300 is 45 kilojoules. Number 5. By the kinetic molecular theory, the heat transfer by conduction. Look, conduction is a way to transfer heat when two objects are touching. And how that happens is when the particles of the hotter object, which are 99, which are all of the time moving faster, and it's obviously in the hotter parts, are gonna collide with the colder parts of the object, but in the colder parts of the object, the molecules there are slower than the ones on the hotter side. With and when these two like molecules collide, that train like the hot molecules give away a part of their kinetic energy to the slower moving molecules. Number 6. During convection, when a part of a fluid of a sample is heated. Okay, now look, convection, I'll explain it by a drawing. But let's say we have this jar of water and we're boiling it over this fire. So here we will have I'll just label it with yellow, split it into two. Here we have the hot, since it's next to the fire. And then up here we'll have the colder, right? And then once there is a difference in temperature, when the water gets heated, for example, in this case, the hot water will become less dense and go up, right? And the moment the hot water becomes less dense, that means the cold water is more dense, resulting it to go to the bottom and then getting heated. This process keeps changing until there is a thermal equilibrium between all parts of the liquid. Number 7. A suspended neutral metal ball touches a rod made of material Y. When a charged glass rod touches the rod made of material Y, the suspended ball remains stationary. Look, when two objects of the same material touch, right, that does not mean there is a change in charge. So like here, it's a glass rod, right? Like when I mean same material, I mean same type conductor, and there won't be a change in charge. But when there are two, or when there is one conductor and one insulator, there is a change. So here there is a glass rod. As we know, glass is an insulator. And since we know that the ball just remains stationary, that means rod Y will just be the same material, which is an insulator. Number 8. In an experiment, a negatively charged rod is brought close to two neutral conducting spheres that touch each other. When one of the spheres, initially standing further away from the rod, is moved away, it is found to carry a charge. Look, so let's just draw it. A negatively charged rod is brought close to two conducting spheres. So here we have a rod that's negative. Okay, now let's start drawing the image that they're trying to explain. So here we have the negatively charged rod, right? And then let's change color to, for the spheres, two natural spheres, right? So let's say, wait, just change the shape. Then here, first sphere, and here we have a second sphere. Touch each other. When one of the spheres initially standing further away from the rod is moved away, it is found to carry a charge. So, but now, okay, now when we move this sphere at the back, it is found to carry a charge. Now look, what happened here is that the electrons moved from the rod to the sphere, and you may ask, how did this happen? Right? Because the rod and the spheres are not touching. So what happened here is induction, which is when charges move from, like in this case, the negatively charged object, the object with more electrons, to the object with less electrons at a distance. So what happened here is that some electrons moved from here, went to the sphere, and then from this sphere, okay, and then from here, as it went here, now it has a charge. Since here again, okay. Look, for this question, honestly, they just want you to get the idea of induction. And then obviously for the second part, there is no way, right? There is no way the sphere would get a positive charge. Come on, guys. Like, it goes from the rod, the electrons go from the rod to the other sphere, and then it goes from that sphere to the faraway sphere. Simple as that. And of course, there is no way that sphere that's away loses electrons. It has the least electrons out of every single. It used to have actually the least amount of electrons in the entire image here. So come on. Number 9. The structure of a thermocouple is shown below. Meter X, wire W, and wire Y, wire Z. Now a thermocouple uses a galvanometer, which we'll find out later is meter X, and two wires, which in this case wire W and wire Y, of the same material, connecting it to a wire, so then which then converts the current or electricity to measure heat. So, and that's what this entire thing does. And the thermocouple measures temperature, as we said. And look, for part B, it's just memorization. You need to know that wire W and wire Y are the same material. You don't need to know what the materials are, but they're mostly copper or constanta. Current X, the meter X measures current. A galvanometer itself measures current, right? A thermocouple is the entire thing. This entire thing is a thermocouple. But meter X is the galvanometer which measures current through these two wires, wire W and wire Y. Which statements correctly describe the thermocouple? Thermocouples have low heat capacities, and thermocouples have a relatively high precision. Number 10. In a circuit, 3 coulombs of charge flow each 0.6 seconds. An ampere, which is current, is equal to coulombs per second. So simply 3 over 0.6 is equal to 5 amperes, which is the unit of current. Number 11. In a circuit, 2 amperes of current flow across a potential difference of 12 voltage for 5 minutes. Okay, fill in the blanks. The power in a circuit is equal to I, which is current, times voltage V. So here, simply all we need to do for power is 2 times 12, and we'll have 24 watts. Done. The energy released in the circuit is energy released in a current is equal to power, which we found in part A, times time. So, and time has to be in seconds, not in minutes like here. So 24 times 5 times 60, that will get you 7,200 joules. But they want it in kilojoules. Do not make a mistake. Do not make a mistake in this, because it will be a silly mistake and you won't be proud of it. So all you need to do now is divide by 1,000 to convert from joules to kilojoules. So you get 7.2. Number 12. Identify the terms that fits the given descriptions. Choose the correct answers. The energy required to turn 1 kilogram of a substance from a liquid into a solid into a liquid state. I mentioned this earlier in the video, and that's the specific latent heat of fusion, which is the energy required to turn 1 kilogram of a substance, like to melt. The energy required for 1 kilogram of a substance to melt or freeze, it doesn't matter. The energy required to turn 1 kilogram of a substance from a liquid into a gas. So we also explained this earlier, and that's the latent heat of vaporization. Number 13. In the diagram below, the current through resistor A is 1.1 amperes and the current through resistor B is 0.3 amperes. Let's analyze this image. So here we have 1.1, hope you guys can see, and here in B we have 0.3. Now look, the in series, right? Let me just write it. Voltage is additive, right? But current is equal, right? And vice versa in parallel, which I just voltage are equal, current is additive. And now, as we can see here, the combination of A and B is connected in series to this lamp over here, which means the sum of A and B, since in parallel current is additive, that means that the sum of the current is going to be equal to the amount of current going through the bulb. So all we're going to do here is 1.1 plus 0.3, which is 1.4. Number 14. In the diagram below, the PET across the battery is 3 volts and the PD across the bulb is 1 volt. Okay, again, same thing as last time, but this time they are using voltage, and again through the combination, which is in series, like the combination of A and B is in series with the lamp, so in series voltage is additive. So, and the battery is in series with the bulb. So the voltage going through the combination will just be simply 3 minus 1, which is 2. So voltage going through the combination is 2. And now since in parallel voltage is constant everywhere in the combination, it's just gonna be that both resistors will have 2 volts going through them. Number 15. The liquid in glass thermometer below is calibrated to be using the Celsius scale. 2 fixed points should be located in the thermometer. Look. Here they're just using the freezing point and boiling point as different names just to confuse you guys, but ice point is the same as the freezing point. It's at 0 degrees Celsius. We figured this out by putting a thermometer in freezing water or melting ice, doesn't matter. And the upper, which means higher temperature, is going to be the boiling point or steam point in this case, which is at 100 degrees Celsius in water, because here they said they were using water, as you can see with the ice, the boiling water. It's all related to water. So again, the boiling point of water is 100 degrees Celsius, and we figured this out by putting the thermometer above boiling water. Number 16. A heat radiator is placed between a white and black surface as shown below. Which surface is better at absorbing heat? Look, to summarize, a black surface is the better absorber and the better emitter. The white surface is only the better reflector. That's it. Number 70. Consider several electric cells connected together. The EMF of each cell is 1.5 volts. Look, since here we can see a cell in the other direction, just cancel the next cell that's in the correct direction, which in this case we'll take is the big one on the left and the small one on the right. So like this. So let's just cancel this and this. So that means we'll have 2 proper cells left, right? So we're just gonna do 1.5 because in voltage again, like in series, voltage is additive. So 1.5 times 2 is 3. Number 18. The resistivity of germanium is 0.48 ohms meter. A wire of germanium has a length of 5 millimeters and a cross-sectional area of 1 millimeter squared. The resistance of this wire is... Okay, look, resistance, there is another rule for resistance, is resistivity, which I'll call it small r, times the length over the area. But everything has to be in meters, since as we can see here, they want it in, like here we have the resistivity in meters. So first let's start off with the length. 5 times 10 to the negative 3, so we can convert it to meters. Just erase this. Times 10 to the negative 3 over the area, which they gave is 1 millimeter squared. To make it easier for the technique, like for the conversions, so here we have millimeter squared, right? So what we're gonna do is act as if we're gonna convert 1 millimeter to meter, right? And then here we see the millimeter squared. Just add that to the power here, times 0.48. And then we're gonna plug that into the calculator. So 5 times 10 to the power of negative 3 over over in brackets 1 times 10 to the negative 3, all of that squared, and then times 0.48. That will give you 2400 ohms. But they want it in kilo ohms, so we divide by 1000 and we get 2.4. Number 19. A current of 3 amperes flows in a 20 ohm resistor for 1.5 minutes. What's the amount of energy? Look, as stated previously in the video, Q is equal to IVT, right? But we do not have voltage. As you can see, we have resistance, current, and time. We just need the voltage. But we know that V, the voltage, is equal to current times resistance. So the voltage is 3 times 20, which is 60. So voltage is equal to 60. So we're gonna do current, which is 3 amperes, times 60 volts. Again, we need the time in seconds, so we do times 1.5 times 60. Just give me a second to plug this in. 3 times 60 times 1.5 times 60, which will give you 16,200. But here again they want it in kilojoules, so you divide by 1000 and you get 16.2 kilojoules. Number 20. Two resistors of resistances 30 and 70 ohms are connected in parallel. Okay. The equivalent resistance of this group of resistors is for in parallel, okay, in parallel resistance is added in a weird way. Look, so you add 1 over the first resistor plus 1 over the second resistor, so on and so forth. But you take the reciprocal, which you can technically say is to the power of negative 1. So simply what you can do here, just plug it into the calculator like this. 1 over 30 plus 1 over 70, the sum all of it to the power of negative 1, and that will give you 21 ohms. Number 21. In the diagram below, the PD across the battery is 24 volts. The resistance of each resistors A and B is 10 ohms, and that of resistor C is 45 ohms. Okay, look, this question is wrong, actually. So I'll just put the correct answers. So over here it's 4.8. And over here it's 2.4. Now look, in my opinion, what I did when I was solving this is I started with part B, trying to find the current through resistor A. So first of all we need to do is to find the current. Actually, we can simply do it like this, because voltage in parallel here, the battery A and B are all in parallel, so the combination is also in parallel. I don't know if you noticed that, but the combination is also in parallel. So simply what we can do is V equals to IR. Now look, we can also say that the voltage in the combination, the resistance in the combination is equal to the resistance of each resistor, and like not combined, like a separate resistor. So you can simply do 24 is equal to I times 10. You get the current of the combination is equal to 2.4. Now that we have that, the current of the combination, right? Wait, what? Wait.